Hi everybody, I'm Brian Hassauer. I'm an Ethernet architect in NPG. And I want to spend a little bit of time just kind of elaborating on some of the things Dave set up there. Really talking about next generation storage networking. Okay, so my agenda is to first spend some time talking about the network latency requirements that Dave kind of introduced a little bit, and what kind of impact those will have when we move storage to non-volatile memory-based storage. And then I want to go a little bit into the network bandwidth requirements that are driven by the cloud storage architecture that Dave showed. And also by the switch to non-volatile memory-based storage. And then a little bit at the end on what is Intel doing in these areas. So, stole Dave's slide. This is a repeat of one he put up a little bit ago. The main thing I wanted to mention about this slide, it's widely known, I guess, that the CSPs are very focused on transactional latency in their different products that they offer, and specifically not only just transactional latency, but the distribution of transactional latency, the tail latencies. And I think this really is driving a lot of these innovation waves that you see here, as they ratchet down and tighten up those requirements for transactional latency. You've seen these moves from traditional networks to flat networks to higher speed networks. A lot of that really is driven by latency. And so this slide goes into a little more detail on that. Again, what we're trying to show here is what would be the read latency for several of the current and next generation non-volatile memory technologies. And I wanted to point out here that, and specifically we have a rule of thumb here that for whatever the media latency is, and you can see here we have 3 rows. One is NVM Express with flash memory, and then a move to 3D crosspoint, and then a move to persistent memory DIMMs. Now these persistent memory DIMMs could be the normal kind of NVDIMMs that are out there today that are DRAM based with flash backup. Or this could also include the 3D crosspoint category. Any event, I'm just trying to do an order of magnitude comparison here. You're going to go from 100 mics down to 10 mics down to 1 mic. And then I'm introducing a rule of thumb that comes from my interactions with customers. They like to try to get to where their network latency is around 20% of what the media latency would be. Now, if you look at this, it's a little bit of a tongue-in-cheek, because as we go from, we're in a realm here with NVM Express with flash memory where 20 mics is feasible, right? As we move down to NVM Express with 3D crosspoint, now we're getting down into 2 mics of network latency, which is starting to get difficult. And then down in persistent memory DIMM land, you're at 200 nanoseconds is a goal that you would have. Well, that becomes very difficult. 200 nanoseconds is 60 meters at the speed of light. So trying to get all of your latency into that is really difficult, especially when you consider this point. The network latency includes commands. Typically in a protocol like NVM Express, you have a command, you have a data transfer, and you have a status message, completion message. And some of those take up to 2 network round trip times to finish for 1 IOP. So really, all of that is included in this number. So our conclusions from this is that we really need, when we start to get to NVM Express with 3D crosspoint, we really need some kind of network acceleration to start to hit these kinds of latencies. And then we're going to have to basically take off all of this, or pull off every trick we can think of to try to get close to achieving this number. And I list some of the ideas here that we have. It's very difficult to achieve these persistent memory DIMM network latencies with an as-is block or file transfer protocol. A new protocol would need to be really minimizing the number of network messages, maximum of a single round trip time to do one IOP. And then we really want to get to the point where there's no CPU interaction, no per IOP CPU interaction on the target. And if we have extra time, I have a slide at the very end. It goes into this in a little more detail. Any questions on this?
So is RDMA active on NVMe Express PCIe Gen 3?
Well, you know, Dave didn't mention it, but there is a protocol extension. Let me just spend a little time talking about this. There's a protocol extension to NVM Express called NVMe over Fabrics, NVM Express over Fabrics. And this is a new standard that's being worked on in the NVM Express work group. Intel is leader, or is one of the people that started this standard, and it's basically a way to surface NVMe drives out onto a fabric with very high performance, and it's a protocol that encapsulates NVM Express across an RDMA network. So
that what?
It's a protocol that encapsulates an NVM Express.
So anything that supports NVMe could support NVMe.
What's that?
Anything to support RDMA could support NVMe over Fabric.
Yeah, the idea is that, and it's a very broad. It's designed to broadly support lots of types of offload networks. The initial focus is RDMA fabrics, including InfiniBand, Rocky, iWarp. But I think there's even some other transports that they're working on as part of that effort. Any kind of network accelerated network, even like fiber channel or something, you could run it over that.
Good, because you can take fiber channel from my cold, dead hands.
Okay, so you know, that would be something that would fall into this category right here. As I said, I think when we get to this category, we're really going to need to try to pick up some of these features down here. Oh, great. Okay, sorry about that. Okay, I'm back. Okay, let's keep moving on here. So this is another slide I stole from Dave. And I don't want to describe too much about this other than to emphasize one point that he made. And I'll just emphasize it. If you look at the drawing of the traditional two-node storage controller here, a lot of the replication traffic is conveyed on this PCI NTB link, and a lot of your replication and rebuild traffic are on all these SAS links, right? So there's a tremendous amount of throughput and bandwidth on these networks, and I'll call PCI a network, but you know, bear with me, it's a two-node network. That all moves when you move from this model to a cloud storage architecture, like Dave mentioned, that moves onto this Ethernet network. And you know, when we couple that, you know, sort of transition with the move to these solid-state drives, there's a tremendous explosion of network bandwidth requirement. And I go into a little bit more on that on the next slide. This is a bit of an eye chart, but bear with me here. What I did was I calculated how many NVM Express drives would be required to saturate various network link speeds using NVM Express over Fabrics protocol. This is just a spreadsheet analysis. So this is like what's the best, you know, what's the best case scenario if you're totally saturating the network with this protocol. And what I'm doing here is I'm actually, if I go back a slide, I'm modeling the network behavior at this node when a write comes in and it has to replicate that write to two other nodes, okay? So again, let's assume we have NVM Express drives capable of 2 gigabytes per second sustained writes, which is not an esoteric type of device, it's a fairly standard device. And we have 100% write traffic with 3x replication, 4K block I/O. So what are the different, how many NVMe drives would be required to saturate a link of these different speeds with that traffic pattern? And what would the IOP and the packet rate be for each of those scenarios? And I won't run through all the numbers on this, but let's just take a look at 100 gig. That's a pretty significant amount of network bandwidth, and yet you can saturate it with, in this traffic pattern, you can saturate that with 3 drives, right? And you're at 13, over 1 million IOPS and over 16 million packets per second for that traffic pattern. So I think this is obvious, right? What are the conclusions? This kind of system will generate massive network bandwidth and drive packet rates high enough to make network acceleration and RDMA type solutions very attractive. Does that make sense? Does that data look real to you guys? Okay, good. Okay, and here's the response that Intel is taking to these requirements. The first thing is that we are integrating RDMA network acceleration into future Intel server chipsets. And this is one of the things I spend a lot of my time on. We are definitely aware of the RDMA latency and bandwidth performance goals that I've mentioned here, and they motivate our designs. And also, we're doing a lot to promote these new storage protocols that I mentioned. So another plug for NVM Express over Fabrics. We're also working very closely with Microsoft on SMB Direct. And in addition, I'm making a little plug here for Nate's talk, which is next. We believe that one of the solutions that we're going to need is very efficient software performance, because when you get to these kinds of massive IOP rates, you really need to drive your software to levels of efficiency that we may not have today. And so that's where this storage performance development kit comes in. It's a specialized product that's somewhat affiliated with the DPDK, and it brings the high-speed packet processing of DPDK to storage. This product is RDMA enabled in the future. When we have these products come out, we'll be able to take advantage of them in this environment. And then another thing that we're working on is very high performance remote access to 3D XPoint technology. We don't want brilliant performance in the box, but you can't get to it from the network. So we're really putting a lot of effort into steps that are going to improve that performance over time. Okay, that's the end of my talk.
So Brian, if 3 PCIe Express NVMe XPoint devices can saturate a 100 gig network, what's a cloud storage environment going to look like? Multiple 100 gig network fabrics out there? I mean, it's one per server is.
I think the cloud providers will probably tell you that their motivation to change network speeds is really focused on latency, and the throughput is going to come when the economics are there. So this is why you're seeing a lot of adoption of 25 gig in the cloud now, because it's very cost effective on a bits moved basis with 10 gig, and it addresses it pushes down on their latency issue, right? Are they going to adopt 100 gig next year? Well, some of them are for some things, but I think in general, all the way to the server or all the way to the storage box, they're going to do it when the economics, the price per bit of moving the data, gets within 2x of where they're at with their current generation.
Storage has historically been a place of, I'll call it speed matching between disk and memory and compute and stuff like that. But it was, a slow technology to a faster technology. With NVMe Express, XPoint, it's becoming almost a reverse of that.
Yeah, that's true. The media is driving us now, which it didn't do in the past. I have extra time, so I'm going to go into my bonus slide.
Okay.
How many bonus slides are we talking about? No.
One bonus slide.
The legal notices. That's.
You know, RDMA has been
but
around for...
You seem to be arguing counter to the DSSD style rack scale switched PCIe model of, concentrating applications close to the data.
Not necessarily. I think what we're doing, if you look at DSSD, I don't want to state too much about their architecture, but it's a very...
But it's PCIe is the interconnect.
It's a very dense architecture, and the scope of that PCI fabric is definitely within a rack, if not less. And so when you go to a cloud environment, they need to distribute that storage at least across a row, if not more, and PCI kind of breaks down there. And that's one of the motivations, by the way, for NVMe over fabrics. The DSSD model stretches the PCI fabric for connectivity to the NVMe drives about as far as it can go. And then after that, you've got to pick something else. And a lot of people are picking Ethernet for that larger scope of connectivity. I just wanted to, like I said, I know RDMA's been around for a long time, and maybe some of the folks here would like a very brief overview on what is it. This is my attempt to make a one slide that describes a fairly complicated piece of technology. So it does have a number of, you have to give me a little bit of poetic license here because I leave out a lot of details, but I want to convey just the high level things about what is RDMA. Really at a very high level, it's a networking performance optimization. If you didn't want to improve your network performance, you wouldn't adopt it. You just keep going with sockets and TCP/IP. It enables servers to communicate across a network using DMA semantics. So if you know what a DMA engine does in a local machine, you can do that now across a network between two machines. And then, of course, it reduces CPU utilization and network-related host memory bandwidth and network latency compared to traditional networking stacks. RDMA NIC resources like send queues, so you can see what send queues and receive queues and doorbells are mapped directly into the application space so that the application can generate network traffic without calling into the OS. This is called OS bypass. So I'm only showing two. The most common RDMA operations are send, write, and read, and I've left read off so you can see my pictures. But send is where you want to convey a command of some type, a message of some type from one server across, in this case, an IP network to another server. So you do that by starting here with this application, posting a command on a send queue. And it defines its message in this source buffer. And these buffers can be, these commands can be issued in virtual address space. So then the network adapter does virtual to physical address translation in this step right here. And it also does all the network segmentation that happens that conveys this message out onto the network. Over on this side, the application is posting empty buffers using a similar technique. These buffers are virtual addresses. And when the messages come in, they get spilled into those buffers through this address translation. So this is just a way to convey messages back and forth. If you want to do the DMA operations that I keep talking about, you want to do something like this, where you've got a source buffer on this side, and this application knows a handle that identifies this sync buffer. It knows it through some out-of-band mechanism not shown here. And so it, again, posts a work request that basically defines a DMA write operation from this source buffer over through the network to this sync buffer. And importantly, one of the things about RDMA that's nice is that there's address translation on both of these nodes, so you don't need to have some kind of global address space that's partitioned amongst the nodes, which means it's fairly scalable as you grow the number of nodes in the cluster. Reads work just like this. They're just a little bit more complicated because the read request will go out on the wire, come over here, the data will get read out of this buffer and then sent back across. Okay, so that's my one one slide, what is RDMA? And now I think I'll be done unless I have some questions.